Hello everyone, I'm Yogeshwari Sandanam representing Group 9 SMJM Section 4 on presenting our assignment 2 on application of second order differential equation. I would like to introduce my teammates Muhammad Afiq Aiman bin Rosli, Christine Fu Jia He, Liu Yong Peng and Aisha Adiba binti Muhammad Astrohomi Joyo. Introduction. Second order differential equations plays a central role in the physical sciences. For example, they are found in laws describing mechanical systems, wave motion, electric currents, and as well as quantum phenomena. Therefore, in Newton's second law, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. For an object in free fall, the net force of it equal to its weight and its weight is proportional to its mass. In other words, if object A has twice the mass of object B, then A also weighs twice as much as B. If a weight A twice as much as B, then the earth pulls on A twice as hard as it pulls on B, and the net force on A during free fall is twice as much as the net force on B.
Problem description. An object of mass falls with velocity from a height above the surface due to gravity and air resistance proportional to velocity. If the distance fall after time is x and the downhill direction is assumed to be positive, the object's motion satisfies the differential equation. In this case, the object falls due to gravity. Galileo proposed the idea that gravity's acceleration at the Earth's surface is essentially constant. Force equal to mass times acceleration, according to Newton's law, implies that F equal to mg, where m denotes the mass of the object and g denotes the gravitational acceleration near the surface. The Newton is the fundamental unit of force in the metric system, equal to 1 kg times m over sec squared. Both m and g are seen as positive.
Hi, next to the methodology overview of the method used to solve the case study. First, we will use the try and error method, which is assume x equal to the exponential of rt and differentiate it twice to get the first derivative and second derivative. The undetermined of coefficient method to solve a non-homogeneous linear second order differential equation. First, find the general solution to the complementary equation. Then, find a particular solution to the non-homogeneous equation. Let y c x be any particular solution to the non-homogeneous linear differential equation, and let c1 y1x plus c2 y2x denote the general solution to the complementary equation. Then, the general solution to the non-homogeneous equation is given like below.
The initial equation given is m d squared x over dt squared plus k dx over dt equal to mg. First, divide the equation with m to get the equation 1. After that, we'll apply trial and error method by assuming x equals to exponential of rt and differentiate it twice to get the first derivative and second derivative. After that, we'll substitute both the derivatives into the equation 1. Factorize out the exponential rt and left r squared plus k over m r in the bracket. And we can assume r squared plus k over mr equal to 0 because exponential of rt can never be 0. So the values of r will be 0 and also negative k over m. Substitute both the value of r into the equation 2 and we will get the value for x1 and x2. For the complementary solution, xc, substitute the x1 and x2 found into the equation below. xc equal to c1 x1 plus c2 x2. Since the initial equation given is non-homogeneous second order differential equations, we will need to find the particular solution xp. To find the particular solution xp, use undetermined coefficient method stated before, which is written as equation 3. Letting r equal to 0 and n equal to 1, we will find that the particular solution xp equal to at plus b. differentiate the xp twice to get the first derivative and second derivative. After that, substitute both the derivatives into the equation 1 to get a value of a. The value of a found will be substituted into equation 4 to get the particular solution xp. And we will get a equal to mg over k. The xp found will be the mg over k times t. To find the general solution, we will need to add both the complementary solution xc as well as the particular solution xp. Differentiate it to get the first derivative, and both the equation 5 and equation 6 will be used to find the value of c1 and also c2. After that, we substitute the condition given in the question for t equal to 0, x equal to 0 into equation 5. As for the t equal to 0, v equal to v0, we will sub it into the equation 6. From equation 5, after we substitute the condition given, we will get the condition which c1 is equal to negative c2 as the equation 7. From the equation 6, the dx dt is also known as the velocity. So we can sub dx dt equal to velocity and then sub the condition given into the equation to get the value of c2, which equal to m squared g over k squared minus mv0 over k. After that, by using the condition given in the equation 7, we will know that c1 is the negative m squared g over k squared plus mv0 over k. Substitute both the c1 and c2 found into the equation 5 and also factorize them to get the final answer.
Result and discussion. In this case of application of second order differential equation, the question shows a situation of where an object with mass m falling from a certain height h with the velocity v0. The initial equation given is where function does not equals to 0, so this makes it non-homogeneous undetermined coefficient. Firstly, we find the first and second derivatives by assuming x equals to e to the power of rt and obtain the general solution xc. In order to obtain particular solution xp, we need to consider the condition for the particular integral, and for this case, it lies under the polynomial function, so this is the general formula to obtain xp. To obtain the final result, we perform an addition between general solution and particular solution and substituted the condition given in the question, which are t equals to 0 and x equals to 0, into equation 5, and also for t equals to 0, v equals to v0 and dx over dt equals to v into equation 6. The final answer will be in terms of x.
Conclusion. Based on the situation discussed using the application of second order differential equation, the determination of the velocity of an object falling through the air, considering only gravity and air resistance, the object's acceleration towards the ground is the acceleration due to gravity minus the acceleration due to the air resistance. Gravity is considered constant and air resistance may be modeled as proportional to the object's velocity. This means that the object's acceleration, which is a derivative of its velocity, depends on velocity. Finding the velocity as a function of time involves solving a differential equation and verifying its validity. Therefore, Newton's law of motion can be applied in numerous situations to solve many problems. And these are the reference for our assignment too. Thank you from me and my teammates Group 9. Thank you.